Alright guys, for lesson 4.7, starting you out on page 371 of your textbook, because I wanted you to see these two graphs side by side. We talked about these as far back as a couple lessons ago. In 4.5 part 2, we went over this inverse graph, this idea of having a one-to-one function, whether it be the original function being a one-to-one function or the inverse function being a one-to-one function. So I wanted to kind of remind you of a basic idea that's going to lead us into today's section. And the idea is when you plug in a number for x, it produces a y value, right? And so early on, when you first learn about the most basic functions, you're taught this idea of input and output, right? We put in a value for x, and the result, the output, is a y value. Well, when you do that with a regular trig function, sine, cosine, tangent, when I say what's the sine of x, what's the cosine of x, the value for x that's going in is an angle, right? If I said what is the sine of pi over 4, right, my input is an angle, and my result, my output, is a length, and that's my y value. Well, what happens when we do an inverse function, right? When you do an inverse function, those things flip, because in an inverse function, now I am putting in a length, and my output, the result, is an angle, right? So an inverse function is asking you for an angle value, and that's why when we're doing an inverse function, they look at this graph, where the domain and the range flip. They trade places, right? Because now my input is a length, and my output, my result, is an angle when we do an inverse function. Okay, so I want you to keep that in mind because this whole idea of domain kind of comes into play here in the rules that we're looking at within these next couple problems. So we'll be coming back to this. Let me jump into the notes. And you probably don't want to look at those upside down, so let me flip that over for you. So here's where our stuff is starting for today. So again, I sketched this, obviously not quite as pretty as the book one, so I wanted you guys to see that. That was on page 371. So we're looking at some of these guys. We're just going to progress our way through these 5 problems right here, because this is ultimately we're leading into this idea. So when we say the inverse sine of negative 1/2, so remember what we just talked about is they are asking me to find an angle for a length or a sine ratio of lengths of negative 1/2. So my input is the negative 1/2. So that's what I'm seeing right here. So my input is negative 1/2, and my output, the result, would be the angle produced in that location, right? And so as I look at let me open up our unit circle real quick. So as we say the inverse sine of negative 1/2, we're asking what angle has a result of negative 1/2, has a sine value of negative 1/2. Remember, sine is our y coordinates. So as I see one right here, and as I see one right here, right, then I'm identifying the angles that produce those answers. So 11 pi over 6 was an angle that produced that answer. 7 pi over 6 was an angle that produced that answer. One of the things that we also talked about in an earlier lesson is in the idea of a one-to-one function, right, what you are going to see as a calculator response, the initial value on this is going to be somewhere between from here to pi over 2, if it's positive, or from here to negative pi over 2 if it's negative. So in our calculator, what we're going to see, it's not going to say 11 pi over 6, right? Even as a decimal, it's not going to say 11 pi over 6. It's going to say, well, let's take 0 minus pi over 6, right? That's our reference angle, is pi over 6. And that's the value that it's going to give us. So when we see that in a calculator, get rid of that. I'm in radians. So when I do the inverse sine of negative 1/2, right, this is the answer that it's giving me. Well, again, where are we getting that from? It's starting at 0, and it's subtracting out the reference angle of pi over 6 in order to get that answer. Right, that's where that's coming from. So remember on this idea, the calculator works from 0 towards positive pi over 2, and it works from 0 towards negative pi over 2. Right? It doesn't go around this way and give you this answer. Right? It works from here up or from here down to get those answers. Right? That's how our calculator works. Now, we know that these answers are periodic. In other words, if my calculator gives me negative pi over 6 as an answer, well, I know if I wanted to turn that into a positive, all I have to do is add 2 pi, and I get 11 pi over 6. I could add 2 pi again and get another answer. I could add 2 pi again and add another answer. Right? These answers are periodic. So what I'm trying to show you is the starting point from the calculator, for what it's giving you to start with. Right? This is the response that it would give you, is negative pi over 6 is our answer. And now if we needed to find more answers, again, we can then add 2 pi or even subtract 2 pi as many times as we want to get more answers from there. So the same thing would happen over here, right? Our calculator is not giving me this answer. What we're going to see is I would have to personally identify this as an answer if I wanted to use it as an answer. Because when my calculator puts me right here at negative pi over 6, I have to understand that is a reference angle. And if that exists here, then it also exists right here. And so I have to interpret that and look at my unit circle and say, okay, I'm also getting that answer at 7 pi over 6. And from there, I could add 2 pi and get another answer. I could add 2 pi and get another answer, or I can subtract 2 pi's and get answers. But it's my job to understand what the calculator is giving me to start with and how I can generate more answers based on my knowledge of the unit circle. Right? And so that's kind of what I'm trying to get at with this. So anyway, let me go back to our examples. So hopefully that made sense. Let's look at another one right here. So in this case, it says, what is the inverse sine of rad 3 over 2? And again, the way we're going to interpret that is from the inverse function right here. Right? It's going to say what angle produces the length ratio of rad 3 over 2. Right? What angle produces that value? And again, if I put that into a calculator, it's going to give me this. Here's my sine ratio of rad 3 over 2. So my calculator is going to work this direction from 0, and it's going to give me an answer of pi thirds if I'm in radians. Or it would give me an answer of 60 if I was in degrees. So that's the one my calculator would produce, right? And that would be my answer. If we needed to find more answers, then again, this is where our side work comes into play, and recognizing a couple things. One would be I could add 2 pi to this and generate more answers. The other idea is pi over 3 is a reference angle. So if I go pi over 3 this direction, so if I go to negative pi over 3, I can generate another answer, right? So I can call it negative pi thirds. I can call it 5 pi over 3. I can add another 2 pi and get more answers, right? So we just want to have that understanding of how to generate more answers beyond what the calculator will provide us to start with. But I'd also mentioned that really the answers that our assignment is looking for today is that answer that the calculator would generate, right? And so that's why, like when you see for the first one, the inverse sine of negative 1/2, this is the answer they're looking for. This is the answer our calculator would generate for us of negative pi over 6, right, when we did part A. So we do need to have the understanding of how to find more answers when asked. But as far as these questions that we're looking at right here, what they're asking for is, what's the answer your calculator is generating, right? What is the answer within this one-to-one function that we're looking at? So that's the answer that we're giving. don't be thrown by this. I know this looks like an angle, but it's not. So, because when I look at this and I see the inverse sine, I know already they're asking me what angle produces this ratio, right? This is a length ratio. Well, if I did, let me just turn that into a normal number for you for a minute. If I did negative pi over 2, here's the length that I'm getting, right? About negative 1.6, we'll call it. Well, what do you notice about my domain here? If I'm within a one-to-one function, I can only work with lengths between negative 1 and positive 1. That's my domain. So I cannot put in a number like negative 1.6 that is outside my domain. So we would have to recognize that for this and say it's not possible, right? This does not exist because it's outside of our domain of an inverse scenario like this. Okay, so let's jump into these guys. These ones are the ones that are really new, and this is kind of where all this is heading. What we are seeing on this is the inverse sine of the sine of pi over 5. So just like any other composite function, we're just working our way inside to outside, right? I want to start with this interior function, and then I'll get to this idea last. So I'm going to start with just the idea of what is the sine of pi over 5. All right, what is the sine of pi over 5? So if I just went into my calculator and I just said, what is the sine of pi over 5? Remember, that's an angle, right? Because I'm now doing the regular sine function, right? I'm not doing an inverse yet. This is a sine function, which means this is an angle. So we're good. And I'm saying, what is the sine of pi fifths? And it's going to give me a length, right? That 0.588 is a length ratio. So I inputted an angle, and the output was my length ratio. Well, now let's look at the exterior function. I need to do the inverse sine of that answer. So I'm now doing the inverse sine of that value. So one thing I want to check is that within my domain, right? If I'm going to do the inverse sine of this, is it within my negative 1 to 1 range? And it is, right? Obviously it is, so I can say, okay, what's the inverse sine of that answer? And I'm going to get this. Notice, that's just right back where I started, right? If I looked at pi fifths as a decimal. So, in other words, we did the sine of pi over 5 to get the length. We did the inverse sine of that length to get the angle back, and it put us right back to where we started at pi over 5. So why did it do that? Well, these are opposites of each other, right? The inverse sine of sine would just be this guy. As we just saw, we went through that process, and it put us right back to where we started at pi over 5. So here's a rule that we're looking at today. So the inverse sine of the sine of x is simply x. If, and here's the big if, and I'm going to show you why it changes when we do part E. The big if is only if the x value that we're putting in is inside this one-to-one function, right? We're putting in an x value that is between those boundary lines of that one-to-one function, and that goes back to what I was showing you in your book, this original graph right here. Remember, this started as the sine of something, not the inverse sine of something, right? This is if you're starting with an inverse. This is if you're starting with the regular function. We're starting with the regular function of sine, and so I'm looking at this. So if the angle that I'm starting with, my input, is between negative pi over 2 to positive pi over 2, then this rule sticks. And we know it's going to work. And so, in other words, I can take a shortcut on this when I see this, and I can just say, oh, my answer is pi fifths. Now I don't have to go through the two-step process of solving for it. So let's look at this guy now and see why it no longer fits this rule. 3 pi over 4 is over here, right? It's bigger than pi halves, so it's not going to fit this rule. Let me show you why. When I do the sine of 3 pi over 4, what is the sine of 3 pi over 4? Let's look at our unit circle. So here's 3 pi over 4. The sine of that is rad 2 over 2. Right? Rad 2 over 2. Well, so what then this is now asking is, let me just write this in. So I figured out the interior function is rad 2 over 2. This is now asking what is the angle that produces rad 2 over 2. Well, the angle that produces rad 2 over 2, as far as my calculator is concerned, is right here. Right? Pi over 4. It's not giving me back what I started with. It's not giving me 3 pi over 4. If I do the inverse sine of rad 2 over 2, my calculator is going to say pi over 4. So, what we need to understand on this one is the rule is not giving me back what I started with. I need to have the understanding of when I was generating this as an answer of rad 2 over 2, remember my calculator works from here to here or from here that direction, right? So I need to answer within the one-to-one function. So I need to give an answer within this area of the graph, right? With somewhere between negative pi over 2 to positive pi over 2. So I need to give an answer in this area of the graph. So I cannot answer with 3 pi over 4. I would have to answer with pi over 4. And so that's why this rule exists as long as you start with an angle within the one-to-one function. And if you're not, then you have to actually take the work, the side work, and do this as a two-step process. Figure out the interior function first, then figure out the inverse function of that answer in order to get your answer of pi over 4. Okay. That was a little more detail than I was intending on, but I think this can be a confusing section if we don't really fully explain that. So here's a couple that you can try on your own. I'll go through them real quick. If you want to pause and try it on your own, I'll follow right behind you. So as I look at these guys, I'm actually going to start right here in my explanation because both of these are outside of the rule that we were using, right? Neither one of these angles are between negative pi halves and positive pi halves. This is bigger than pi over 2, and this is bigger than pi over 2. So I can't use the cheat rule, the shortcut rule on either one of those. Here I could have, right? On this one I could have, because pi over 11 is between negative pi over 2 and positive pi over 2. So when I see this, I can just simply answer with, oh, my answer is pi over 11 because it fits that shortcut. But these don't fit that shortcut. So I can't take the shortcut on either one of those. This is one we need to include in the future for sure. So I need to figure out, okay, what's the sine of 2 pi over 3? So what's the sine of, here's 2 pi over 3. My sine value is rad 3 over 2. Now I need to do the inverse function, the exterior function, and say, okay, what angle produces rad 3 over 2? Now I need to look over here within my one-to-one function, right? And now I'm looking at this saying the angle that produces this is pi over 3, right? So I want to answer within my one-to-one function. So same thing on this one. I would say, what's the sine of 5 pi over 6? What angle? Well, sorry, what side length ratio? So the angle is 5 pi over 6, so the side length ratio is 1 over 2. So then now we do the inverse function and say, okay, what angle produces the ratio of 1 over 2? And that's what puts me back within my one-to-one function, and I would answer with pi over 6. And if you put all this into your calculator, this is the answer it's going to give you, right? It's not in a decimal. It's not going to do it in terms of pi, but it's going to give you pi over 6 as a decimal. Let's move on. So let's branch out to our cosine function and our tangent function. So again, I want you to see the idea of the domain and range for these guys. So if you look at page 373, let me go 2 pages to the right here. All right, so here is our cosine function. So for cosine, a little different, right? This is the original one-to-one function of the cosine graph, right? So our domain in cosine goes from 0 to pi. And we did talk about this in an earlier lesson. It just didn't look like this. I showed you this way. If you look at your unit circle, sorry, let me do this. The cosine graph goes from here to there, right? It goes from 0 to pi. So your one-to-one function for a cosine function goes from 0 to pi. So if it's positive, it'll be right here in quadrant 1. And if it's negative, it's going to be right here in quadrant 2, right? But that's how the one-to-one function works for cosine. When you put something into your calculator for a cosine value, it's going to give you an answer somewhere between 0 and pi as an answer. That's the original value that we would get from a calculator. Like I already mentioned, you can get more answers than that, but this is the one that we would start with, right? This is what the calculator would produce within the one-to-one function. So the inverse function, if I'm going to do an inverse cosine graph, remember when you do the regular, your input is the angle and your output is the length ratio. Well, if the inverse function exists, here's the one-to-one function for the inverse, and it's just the reciprocal of this, right? My domain and range trade places. So now my domain for the inverse function is between -1 and +1, just like it was for sine. But my range, my output, is from 0 to pi, like I just showed you on the unit circle, right? So when I do an inverse, I am putting in a value between -1 and 1, and my output is going to be an angle from 0 to pi. So let's look at a couple of these. So what is the angle that produces the length ratio of rad 3 over 2? So we are putting in the length ratio, and the result, the output, is going to be an angle between 0 and pi. So we are putting in rad 3 over 2. So remember, cosine is your x's. So we are putting in an x value of rad 3 over 2 right here. And the angle that we would get out of that is pi over 6. Like I mentioned, there are other answers, but not within the one-to-one function. And all we're looking at for right now is what is the initial answer within the one-to-one function. So we would answer with pi over 6. What about our tangent function? So let me take you to the tangents real quick. Tangents work a lot like the sine function does. Here's your tangent. So tangents work this way. Your domain of the original tangent function is -pi over 2 to +pi over 2. But the results, the length ratios, are unlimited. They're infinite, right? The range on this is infinite, which means if you do the inverse, I can put in any side length I want. I can put in a length ratio for tangent of anything, any number between -infinity and +infinity. The result, just like the sine function, is going to be an angle between -pi over 2 and +pi over 2. So for my tangent function, they're saying what angle produces a length ratio of +1. So when I look at that, remember that I can only answer from -pi over 2 to +pi over 2, right? And in that regard as well, it's not inclusive, right? It's got to be between -pi over 2 and +pi over 2, not inclusive, because in the original function I had vertical asymptotes right there, right? It didn't exist. I have an asymptote there and I have an asymptote right there. So this is non-inclusive. It has to be a number between here and here. So when we look at that, where would we find +1 as far as the tangent function goes, right? And I'm seeing that right here. Remember, tangent is sine divided by cosine, y divided by x. So if I did this divided by this, I'm going to get 1. So my answer is simply pi over 4. It does exist in other places, right here. I would also have a tangent function of 1. My answer would be 5 pi over 4, but again, I'm only answering within the one-to-one function, which is right here, right? I'm either going 0 up or I'm going 0 minus to get my answers. So for this guy, for part C, again, I'm now back into the inverse cosine of the cosine of negative 1.5. So here's the rule that we see, very similar to the sine function, with one little difference, and that's this. So the shortcut only exists in the cosine function if your angle is between 0 and pi. Right? Because remember, this means the cosine of this angle, and then I would be doing what angle produced that answer. So in this case, again, I get the shortcut if this exists. Negative 1.5 does not fit within that domain right there. So I would have to kind of take the two-step process by hand in order to figure this out, because the shortcut doesn't exist unless this is true. So we can still say, what's the cosine of negative 1.5? In other words, the cosine of the angle, negative 1.5, gives me what length? Right? I'm getting a length answer out of this because this is negative 1.5 is the angle. So in a case like this, I would have to do this one by calculator. This is not one of our unit circle values. We don't have that as a radian angle. So I'm going to show you sort of the calculator and the non-calculator way of getting this. Of course, we could put this into a calculator, right? And I could say, what is the inverse cosine of the cosine of negative 1.5? Right, I can set it up just the way it was presented to me and get my value of 1.5. Notice on this one, I am not getting back what I started with, as we've already talked about why that rule is not going to work for this one. So how could I have done this without a calculator to figure this out? And it all comes back to reference angles as we look at the unit circle. So negative 1.5 is not one of our typical radian angles that we would see on this unit circle. I'm not going to see negative 1.5 here. So this is where my understanding of reference angles comes into play. So if I am looking at the angle of negative 1.5, right, which is going to put me down here somewhere. So if I said negative 1.5, where would I find that within my one-to-one function, right? So if I need the answer between 0 and pi, so I'm going to understand that if my reference angle is negative 1.5, that means I can also do positive 1.5 here to get my answer. And positive 1.5 is within my one-to-one function, right? So I'm going to recognize that simply negative 1.5 is my reference angle. So therefore, positive 1.5 is also the same reference angle, but this direction, which is in my one-to-one function. And so I'm going to give the answer of positive 1.5, just like my calculator did. Right? And that's where they got this. So they're treating that downward value of 1.5 as simply the reference angle. Remember, negative 1.5 simply means that I'm going 1.5 units this direction. Positive 1.5 means I'm going 1.5 units this direction, right? And so I want to treat it as going this direction so that I'm within my one-to-one function. Okay. So almost done. We're going to peek at a couple problems together just for practice, and then I want to show you one last problem, and we'll be good to go. So anyway, so now when they say, okay, what's the inverse cosine of negative rad 2 over 2? In other words, what angle would produce the length ratio of negative rad 2 over 2. And remember, for this, we want to answer with a value from somewhere between 0 and pi, if we're doing this correctly, is our initial angle here. So what angle produces the negative rad 2 over 2? Well, as I look at this, negative rad 2 over 2 is an x. So here it is right here. So the angle that I'm seeing is simply 3 pi over 4. And again, just to reiterate what we're looking at here is there are other answers. I see the same answer right here. And that would be the angle of 5 pi over 4. So more answers do exist. But for these purposes, we're only seeing the initial one-to-one answer. And so we're only going to give 3 pi over 4. For the inverse tangent of negative 1, so what angle produces a tangent length ratio of negative 1? So what angle? And remember, for tangents, tangents work from here to here or from here to here. So where do we see that tangent issue? I'm seeing it right here. Remember, if I did my y divided by x, I would get -1. And so I want to give the answer of not 7 pi over 4, right? Remember, the tangent function goes from 0 in the negative direction towards negative pi over 2, right? It does not go from here to here. So we can't give 7 pi over 4. What we need to see is, how do I get from here to here? Well, I would subtract pi over 4 in order to get this, right? So our answer would be negative pi over 4. Moving on into this guy, again, remember arc cosine is the same thing as the inverse cosine of whatever I'm finding here. And so we're now looking at just another composite function. And they're saying, okay, now there's no rule that fits this, right? We haven't seen any rule that fits different ones. We can still do it. So we'll start with the inside and work our way out. So I need to figure out what's the tangent of pi over 4. Let's just start with that. So the tangent of pi over 4, if I did sine divided by cosine, is 1. So they're saying, okay, what is the, I'll fill it in as we go. So what is the arc cosine, or what is the inverse cosine of 1? So what angle produces a cosine length of 1? So as we already know from our unit circle right here, so our cosine length of 1 is this guy right here. So it would be 0 degrees, or we could say 0 radians for that guy. Let me go back to this. So one last one. Again, if I wanted to do the inverse cosine of the cosine of negative 1.8, as we already saw, the shortcut for this only exists if the value that I'm putting in for x is within the domain of 0 to pi. This is not a number between 0 and 3.14. So I can't take the shortcut and say this is my answer, but as we saw in the previous problem, up here, we're just treating this as my reference angle. So in other words, if I go 1.8 radians this direction, so if I understand that 1.8 is a reference angle, then that means I can also go 1.8 radians this direction and state my answer from there. So my answer would simply be 1.8 because that is the value between 0 and pi that we're looking for. So let me show you one last thing. All right, so last one on these. So I just felt like you needed to see this for a homework problem today. So in this case, they're telling me what is the cosine of theta, what is the cosine of the angle if the sine of the angle is x. So if you think of our basic triangle like this, we're saying we know the sine ratio is x over 1. So if I did from here, if I did opposite over hypotenuse, I'm seeing this relationship right there. Now I'm actually going to change my drawing now that I'm thinking about it, because I think this will help you understand the final step of this problem. So I'm actually going to draw it right here, so you can see this a little more clear when we get to the final part of this. Right, so again, from within this drawing, I'm going to say opposite over hypotenuse. So I need to come up with this length right here. So for this guy, if I use my Pythagorean theorem, so c squared equals a squared plus b squared. I guess I'm calling this b. Right, we need to come up with an expression for him. So if I solve for b on this one, so I'm going to subtract my x squared over, and then I would have to square root to get b by itself. So we're going to say this. And of course, typically we would have to answer with a plus or minus scenario on that. But however, if you think of where this would be drawn, my sine values, as we already saw, work within this area right here, right? So I can only draw this within quadrants 1 or 4. Either way, I am traveling to the right. So if I drew it in quadrant 1, I'm going right and up. If I drew it in quadrant 4, I would be going right and down. But in either scenario, I'm going to the right. So this has to be a positive value. So we can exclude the negative option on this and just call this positive 1 minus x squared. So that it looks like this. Now I can say, okay, so then from that drawing, what is the cosine of theta? Well, the cosine, if I do adjacent over hypotenuse, would simply equal the square root of 1 minus x squared. And that's it. So lots to take into account in this as far as where you would draw it and the idea of it being positive or negative, but that's it for lesson 4.7.